So, since we were talking about this positive and zero and negative numbers, so let me just mention that Brahmagupta had also given this rule for the square root of binomial surds. But now my actually topic is equations. So, to appreciate again to get the chronological perspective of the work on equations done by Brahmagupta and successive mathematicians, and also to realize that how far Indians were ahead in algebra, and people talk about Arabs having invented algebra, but this so called after the invention of algebra by Arabs which goes to Europe, just think of how algebraic problems were solved by the Arabs and early Europeans. So, this pre-algebra, before algebra came to Europe in a big way due to Vieta, Descartes, etc., how they used to solve problems. And then you will see that how hollow this claim is about Arabs doing algebra. So, the problems involving simple linear equations of the form A x plus b equal to c I, where A, B, C are all positive, as you know that the negative numbers were not used, created difficulty among Arab and European mathematicians till 14th to 15th centuries. So, let me pose a problem. I have invented this problem, so to keep matters this simple. Suppose 170 apples are distributed equally in 8 closed boxes and 2 are in excess. How many apples are there in each box? These are practical kind of questions, and because of our training with equations, we immediately think of it as 8x plus 2 equal to 170. But suppose this thing was not there. In fact, this framing of equation culture came much late. So, before that, what was the approach? It is called rule of false position, regula falsi. Now, to state the rule verbally would become unwieldy. So, I will use the algebraic notation to state the rule, but you have to read it without the notation. Just keep in mind that the notation is not there. So, rule of false position says that you guess a value for that unknown. So, if 170 apples are distributed in equal enclosed boxes, then what is the likely value, likely number of apples in each box? So, suppose you guess that it is 20. Then what you do is that had 20 been the correct answer, then what would be the total number of apples? You make the calculations. So, it would come out to be 20 into 8 and there are 2 in excess. So, it is 162, but the total number is 170. So, you see that there is a error. So, you compute what is the error, and then the correct value would be that you look at the guessed value, that is 20, then look at that error and divide it by the number of boxes. Oh, there is a typo here. It is not 1 by 1, it should be 8 by 8. 20 plus 8 by 8, then the meaning will be clear. So, it is 21. So, this is the such a convoluted rule that people used. And then there was another rule called rule of double false position, that you guess 2 values. So, now I will just purely use algebraic notation to save time. So, guess 2 values u and v and then compute that had the value been correct, then what would have been the total number. So, this 2 values would give you p and q, then determine the errors E u and E v, then you look at this v times E u minus u times E v divided by E u minus E v. Now, as late as middle of 16th century, Robert Recorde, who is highly respected as author of textbooks in arithmetic of that time, thought highly of this rule. So, it is when you are thinking, this is 1542 and Brahmagupta's time is 628. So, To appreciate this Brahmagupta's algebra, you keep in mind the general development of algebra in the rest of the world, including this Arab and early European world. This is how problems involving simple linear equations were addressed. However, one should also point out here that this rule of false position should not be made fun of, because it led to something very profound, meaning the fact that they did not have algebra, the Indian type algebra, and they struggled with this rule of false position. Therefore, they prepared the European mind for something profound, that is the Newton-Raphson method. So, what they were doing is, so Newton-Raphson method is for an arbitrary function, but if you take linear, then what does Newton-Raphson method tell you is precisely this rule. So, they had worked out Newton-Raphson for the linear case, and once you have it for linear case, so after all the Indian method of doing algebra will not work if the function is arbitrary. So, it is really this Arab and European method which would work, this rule of false position, that is try to generalize and you get this Newton-Raphson. Because you may wonder how this is coming up, because if you think of it geometrically, the rule of false position, then what it is doing is that you have a line and you are kind of approximating it, going step by step, and that is what you do, you replace the line by an arbitrary curve. But however, if it is really linear, you do not obviously need Newton-Raphson. This basic algebra makes it so easy. So, this difficulty, though this was a very productive difficulty, but this difficulty was due to lack of algebraic symbolism from Al-Khwarizmi onwards, concept of formation and processing of equations and use of negative numbers. So, these pillars of classical algebra had been developed in ancient India by the time of Brahmagupta. Once the concepts got standardized, the solution of the linear equation became easy. Now, okay. Oh, I forgot to delete this page. Now, first I summarize the development of quadratic equations. So, the general formula for the solution of the quadratic equation, the strategy is to eliminate the middle term, and this is called madhya. Madhya means middle and harana means eliminate. So, this is given by Brahmagupta, and the idea, how do you eliminate the middle term? This idea was, this completing the square, that idea was explicitly given by Sridharacharya, that is what we believe, because Sridharacharya's book in algebra has not been found, but Bhaskaracharya has attributed it. So, ax square plus bx equal to c, multiply by 4a, and then you get 2x plus b whole square is b square minus 4ac. And then what happens is, setting y equal to 2x plus b, the equation reduces to the form y square equal to d, where y is a known quantity, and so it reduces to solving the linear equation 2x plus b equal to y, and by that time the solution of linear equation was known. Now, one thing should be made clear, that this attribution should be made correctly. So, Brahmagupta, what is special about Brahmagupta is, he is first to describe the formula in the general context, that means without any reference to anything. But this should not be mistaken as saying that it was Brahmagupta who invented how to solve the equation. The two are different. To state the solution explicitly without any specific context is what Brahmagupta does for the first time. but the formula was known, it was not written, but it was known to the author of the Bakshali manuscript, which is the date is not determined as precisely as the date of Aryabhatta or Brahmagupta, but let us say 3rd century. And Aryabhatta definitely 499, Aryabhatta knew the formula. So, Aryabhatta describes it when this A, B, C are quantities in problems on arithmetic progression or problems in interest. So, it is given in specific context, because Aryabhatta has not introduced algebra. So, when it is needed, he gives it. So, he knew how to solve, but why he has not given the general solution? Because the question of equation and giving the roots, that question did not arise, because algebra has not been formulated by Aryabhatta. So, Brahmagupta describes the formula for arbitrary A, B, C, uses the term Madhya Harana, elimination of the middle. Obviously, he knew the method of elimination, that means completing the square. But here again comes that Brahmagupta has not specified that how he has got that multiply by 4a. He has not said that, he has given you the final answer. So, saying that is a service to the humanity. So, that was given by Sridharacharya, that he describes the method of completing the square, which so Aryabhatta knows how to solve, but he does not say it. Brahmagupta tells you the root in arbitrary context, but he does not show you how to obtain it. Sridharacharya shows you how to obtain it, but then his treatise is lost. And Bhaskaracharya quotes Sridharacharya's method of completing the square, and this is a profound idea of far-reaching significance. And Abhyankar is very fond of quoting Bhaskaracharya's verses on completing the square. Now, thanks to the use of negative numbers, Indians gave unified treatment, whether it is Brahmagupta or Bhaskaracharya, unified treatment of the solution of quadratic equations, and for a long time in Arabs and in Europe, 3 different cases were studied separately. Ax square plus bx is c, x square equal to bx plus c, and ax square plus c equal to bx, where a, b, c are positive. Now, the importance of the idea of elimination of the middle. So, you see, for x square plus bx plus c, the substitution y equal to x plus b by 2 eliminates the middle term. Brahmagupta knew it and Sridharacharya spelt it out. So, likewise, the same principle will give you, instead of b by 2, if you take b1 by n, then you can eliminate the coefficient of x to the power n minus 1, and this is called the Schönhausen transformation. Now, in his survey article, Abhyankar points out that this killing of B1 was the basic trick underlying Zariski's and Hironaka's proofs of resolution of singularities of algebraic varieties of 0 characteristic. And there is a theorem of Newton on the power series ring. So, Abhyankar gave a certain proof of that, and that proof, which is Abhyankar's proof, he calls it Sridharacharya's proof, because the basic idea is this completing something. So, he gave this tribute, Sridharacharya's proof. Now, just to see what exactly Brahmagupta has said, that Varga Chatur Gunitam Rupanam. So, Rupa is the visible thing, that is C. So, the absolute quantity multiplied by 4 times the Varga is square, Chatur is 4. So, the absolute quantity multiplied by 4 times the coefficient of the square of the unknown, Varga Chatura Gunitanam Rupanam Madhya Varga Sahitanam. So, the absolute quantity multiplied by 4 times the coefficient of the square of the unknown are increased So, Moolam is that square. So, multiplied by 4 times the coefficient of the square of the unknown are increased by the coefficient of the middle. So, what is happening? The absolute quantity, that is C, multiplied by 4 times the coefficient of the square of the unknown. So, 4 times AC are increased by the coefficient of the middle. So, for AC,
I think we should write it
yeah.
in Devanagari script, the Sanskrit verses.
Yeah, I don't know. I mean, that is a, I mean, this, I don't have that.
If I am correct, it is Varga Chatur Gunitanam Rupanam
Madhya,
Varga Sahitanam.
Varga is square, Sahitanam. So, Madhya is that B and then you Varga, that is square. So, it has to be 4AC plus B square. And then square root of the result, that means root of 4AC plus B square diminished by the coefficient of the middle. So, that means root 4A square plus BC, then you diminish it minus B and divided by twice the coefficient of the square of the unknown. That is the value of the middle. Middle is that unknown. Now, to set the, just as you know, I was saying that, you know, trying to, because of the popularity of Lilavati, that everything, oh, Indians knew it. What is the proof? It is there in Lilavati. So, people come to the conclusion that all these things were done in 12th century. So, we should not make this error of attributing everything to Brahmagupta when things were known before that. So, merit of Lilavati is the beautiful formulation, not invention. Similarly, Brahmagupta is not the person who invented how to solve quadratic equations, make no mistake. So, I will now give the corrective that who are the people who knew how to solve quadratic equations. Look at Aryabhata. Aryabhata has given the formula for finding the number of terms of an AP series whose first term A, common difference D and the sum are all known. Now, what Aryabhata has given is this formula. That is it. That is all that you get in Aryabhata. Now, if you read between the lines, that how does this n arise? This n arises as the root of the quadratic equation. So, this x is the, so this number of terms is unknown, but first term, common difference and sum is known. So, normally what happens is we know the number of terms and write down the sum, but suppose it is the other way, that you know the sum and from that you have to deduce the number of terms. That is what he says. So, in that case you have the quadratic equation. Aryabhata does not written the quadratic equation dx square plus 2a minus d into x equal to 2x, but we know that this is a quadratic equation satisfied by all these things, and the solution of that quadratic equation is this. Now, when you finally see that Aryabhata has written this as a formula for number of terms, you know that Aryabhata knew how to solve the quadratic equation. He knew the formula for the roots, but he has not said the formula. This cannot be called as a formula for solution for ax square plus bx plus c. Therefore, we are not in a position to quote Aryabhata, therefore, we have to quote Brahmagupta only. And not only that, the formula also appears in the Bhaskara treatise. Another problem solved by Aryabhata. Aryabhata has also given the solution to a problem on interest. So, all this is arithmetic. So, suppose interest is I, principal is P, time is T and amount is A. All these are known, but interest is unknown. Now, the formula, so this Tx square plus Px equal to AP, that is something that we know. I mean, the relationship between amount and principal, time, etc., will give you this Tx square plus Px equal to AP. And the solution of that is this. But what you find in Aryabhata is that he just says I equal to root APT plus P by 2 whole square minus P by 2 by T. Now, somebody who has given this formula, obviously he knows the solution of the general quadratic equation, but since he has not introduced algebra, he is not in a position to talk about the general solution. Similarly, the author of the Bakshali manuscript also knew the solution of quadratic equation.
Simple interest, right? Not compound
It
interest.
is actually interest on interest. It is probably somewhat different. He has
Yeah.
not mentioned it completely.
Yeah, the interest keeps on.
It was some
Yeah.
It is simple interest or compound interest?
No, interest will keep on accumulating. I mean, see, this has this.
Compound, it's compound.
It is compound. Yeah.
So some of the exponential doesn't arise there. So exponential, this leads to exponential. Leads to
If you compound it several times,
Several
then
times,
in
then
every
it
case
is
it's
exponential.
exponential.
Now, there is this complicated problem in Bakshali that a certain person travels a yojana on the first day and B yojana more on each successive day. Another who travels at the uniform rate of C yojana per day has a start of T days. When will the first man overtake the second? Now, what happens is that if you just let me just cut the story short. The details are given in my article. So, if you try to solve the problem by the by your methods, then what you will land up with is this quadratic equation, and the solution of that quadratic equation is this, and what you find in Bakshali manuscript is the final result. So, the author of the Bakshali manuscript knew how to solve quadratic equation, but he has just given this formula, and that too in words. So, this is the picture. So, I would put it that Brahmagupta's formula for quadratic equation is also a part of his contributions to the foundation of algebra. It is not that quadratic equations were being solved for the first time, but to it is a contribution to state it in terms of arbitrary coefficients, that means in arbitrary context, which is again solidifying the approach to algebra. I mean, this becomes a step to firmly implant algebra in the Indian mind.
So before Brahmagupta, they used to do it again and again in every application.
Yes, yes.
So
And that
solve quadratic every time.
Madhyaharan is
Hmm?
something,
Which one?
Madhyaharan,
Hmm.
middle term algebra, that is used even now. Everybody says that
Yeah.
method is that only.
Yeah, so Madhyaharan, the point is that you can call it Sridharacharya's method, but again Brahmagupta knew the method, that's clear by his term elimination of the middle.
Yeah.
For quadratic, it is actually the middle. For higher degrees, it is one of the terms. It is just
The n minus 1 term.
second term.
Yeah.
This Madhyaharan is also before Brahmagupta, or?
No, Brahmagupta uses the term Madhyaharan. So before that nobody has stated the formula for quadratic thing. So they have used it and giving you the final answer.
So one doesn't know how they have found.
But it comes in geometric algebra
Which
in
one?
a different way.
Geometric algebra, they are doing it geometrically. That's a different ball game altogether. See, geometric algebra, they are also solving linear equations like Ax equal to c square. That is mentioned even in Jawaharlal Nehru's Discovery of India. But Ax equal to c square, they are not solving by saying that x equal to c square by a. They are solving it geometrically. So, they are giving you a geometric construction.
Quadratic is
Quadratic, it is not the arbitrary quadratic, but some problems involve quadratic equations or certain forms of quadratic equations. So, you can interpret it as solutions of quadratic of a particular form of quadratic equation. But it is again, it is not an algebraic solution, it is see basically when they are solving it, they are kind of geometrically looking at certain equation, but the perception is purely geometric, and you don't get the algebraic answer eventually. Yeah. Yeah.